So this lesson is for CHM 605 polymer chemistry. We're looking at the preparation of polyamides. We briefly reviewed the formation of a polyamide by the reaction of an acid chloride plus an amine, an acid anhydride plus an amine, a carboxylic acid and an amine, and the ring opening of a lactam, that is a cyclic amide. Just to remind ourselves, among the carbonyl groups, the acid chloride is in fact the most reactive of the carbonyl compounds, and so reacts very quickly with an amine, followed second by an acid anhydride. And then a little later we see carboxylic acids further down the group in terms of reactivity. Here's the mechanism for the reaction of an acid chloride plus an amine. Being the best of electrophiles, it can accept a pair of electrons from even a moderately good electron donor, like an amino group. The pi bond is the weakest of bonds in here and will break, and it will reform if there's a leaving group, and in fact there is. Chloride is a good leaving group, and so that adds the amino group, and then there'll be ultimately a proton transfer from the amino group, producing the neutral amide molecule. I won't rediscuss the need for tertiary amine to avoid consuming of amine reagent. The second most reactive of the carbonyl groups is the acid anhydride, and once again this fair nucleophile amino group can react quite readily with the carbonyl of an acid anhydride. The pi bond will break to make room for the pair of electrons from the amine, and the pi bond will reform if there's a leaving group, and in fact there is. In this case, the leaving group will be a carboxylate. The carboxylate will ultimately deprotonate the protonated amide to make a neutral amide and a carboxylic acid. Now you can work directly from the carboxylic acid and the amine. This is certainly the cheapest route because the carboxylic acid is a much cheaper reagent than the acid anhydride or the anhydride. This is simply an acid-base reaction in which the amine, being a base, abstracts a hydrogen ion from the carboxylic acid, producing a carboxylate and an amine, and then on heating it condenses out water to produce the neutral amide. Not elegant, but certainly the most economical approach, and that's the one that's used very commonly in industry. We also looked at the ring opening of lactams using a very strong base like sodium hydride, deprotonating the weakly acidic hydrogen on the amide, producing then a nitride anion, which can react further with other lactams to ring open them and producing an open chain amide. So that's a bit of a review. We were starting to look at the naming of nylons, and we want to go through that in some detail. So much of this is in the notes, but there's some things for you to fill in here. So polyamides, discovered somewhere about 1930-ish by Wallace Carruthers, the father of polymer chemistry. Polyamides have the characteristic amide functional group, R carbonyl N whatever. Interesting that the first commercial market for this very important polymer actually happened to be women's hosiery. So nylon is simply DuPont's trade name for aliphatic polyamides, and Aramid is the generic name for a fully aromatic polyamide, which I'll explain in some detail in just a little bit. But let's get an overview of the type of nylons that are available. The simplest possible nylon would be one that has only one carbon in the repeating group, and hence it's called nylon 1. So nylon 1 has one carbon in the main chain of its mer, its repeating unit. So an isocyanate can be used to form that, and this is not part of what you're responsible for, but I just want to include it for sense of completeness. The nylon 2 would have two carbons in the main chain of its mer, as we see here. And any of the alpha amino acids, that's an amino group on the alpha carbon, can in fact produce a nylon 2 type polyamide. And that is in fact what's done in nature in the formation of silk by silkworms and spider webs by spiders and fabrication of proteins by living beings. More to the commercial side though, nylon 3 would have 3 carbons in its repeating chain, and there is a somewhat commercial process involving nylon 3. It starts with this cyclic amide. We did spend some time reviewing nomenclature, so I'll just talk about it. You'll find the instructions for that in the appendix of this unit if you haven't looked at that, if you missed that course. But in any case, in the IUPAC system, we number from the carbonyl. Carbon is the highest priority, 1, 2, 3, and 4. The longest carbon chain is 4. And so we name this as 3-amino and 3-methyl. Butanoic acid, the longest carbon chain is 4. Lactam. So lactam just means it's the cyclic form of the amino acid. Now in the common system, they do have a locant system for 5 carbons, alpha, beta, gamma, delta, epsilon. Alpha is the carbon next to the carbonyl carbon, so that's alpha, beta. And so this would be called beta methyl and then beta amino, butyrolactam. But because it's the common system, we tend to abbreviate names. There's no reason to say beta amino because it had to be amino group to form a lactam, so that's left out. We simply leave the locant where the amino group was, so it's beta methyl, beta butyrolactam. Again, I refer you to the page on naming lactams if you didn't catch that earlier. So, to name the polymer, when this ring opens, in the IUPAC system, it's simply polymesomer. Here is carbon 1, 2, 3. This would be 3,3-dimethyl propanamide. Poly, 3,3-dimethyl propanamide. In the common system, it's polymonomer. And since we know the monomer's name is beta methyl, beta butyrolactam, therefore the polymer's name is poly beta methyl beta butyrolactam. Nylon 4 also comes by ring opening of a lactam. Now this will be carbon 1, 2, 3, 4. That would be therefore 4-amino butanoic acid, 4 carbons in total, lactam. Now in the common system, this is alpha, beta, gamma, 4 carbons in total, butyrolactam. So alpha, beta, gamma, butyrolactam. Don't worry about the pyrrolidone, that's a non-systematic other historic name. So to name nylon 4, in the common system it's polymonomer, and therefore we'd call this poly gamma butyrolactam. In the IUPAC system it's poly repeating unit. This is simply a 4-carbon straight chain amide, and therefore it's polybutanamide. Nylon 5 is also produced by ring opening a cyclic amide, a lactam. Here we have carbon 1, 2, 3, 4, 5. So we name that as 5-amino pentanoic acid lactam. In the common system, this is carbon alpha, beta, gamma, delta, and 5 carbons is valeric acid, so that's delta valerolactam. Again, don't worry about the pipyridone, that's another non-systematic common name. When this ring opens, we get a straight chain 5-carbon polyamide. In the IUPAC system, poly repeating unit would simply be polypentanamide, or in the common system it's polymonomer, hence that's poly gamma valerolactam. I might make a believer out of you yet that the more of these you do, actually the easier it is to do. It works that way. Nylon 6, one of the most important of all the nylons, made by either ring opening a cyclic amide lactam or from an open chain amino acid. Let's look first at the lactam. This is carbon 1, 2, 3, 4, 5, 6. That'd be 6 amino hexanoic acid lactam. Or in the common system, this is alpha, beta, gamma, delta, epsilon. So we'd say E, caprolactam, capro from caproic acid with 6 carbons. And so to name the polymer, an unbranched 6-carbon polyamide would simply be hexanamide, so we have polyhexanamide in IUPAC. In the common system, it's polymonomer, so that would be poly-ecaprolactam. Now, nylon 6 can also be made by polymerization of an amino acid with a carboxylic acid functional group and an amino group on the same molecule. And so this would be 6-amino hexanoic acid. The common name for this amino acid would be E-amino caproic acid, not the lactam, simply the open chain form, and then the product name would then be poly-E-amino caproic acid, as opposed to poly-ecaprolactam. These are in fact the very same polymers, but derived from 2 different monomers, so the names really are equivalent. So nylon 6 is actually the second largest production among the nylons. You'd recognize it as a material used in bristles of brushes, for example, like paint brushes. Nylon 7 also derives from an open chain amino acid. 7-amino heptanoic acid can be polymerized to poly, so this is 7-carbon open chain, unbranched, polyamide, polyheptanamide. Now, locants. We had alpha, beta, gamma, delta, and epsilon. That's as high as locants go in the common system, unless there's a locant on the last carbon in the chain, and that is higher than E. So if it's beyond E, or epsilon, and it happens to be on the last carbon, it's called omega. Omega being the last letter in the Greek alphabet. So in this case, our amino group is on the last carbon in the chain, and it's beyond the E position, so it's called omega amino enanthic acid, enanthic being a 7-carbon acid. You don't have to learn the name of enanthic acid, it's less common, but I want to present it for completeness. The polymer name therefore would of course be polyheptanamide, or if we knew the monomer name, polyomega amino enanthic acid. Well, we're getting longer here. Nylon 11. 11 is undecanoic, if you recall your basic nomenclature. Undecanoic acid has 11 carbons. If there's an amino group on the last carbon, it would be 11-amino undecanoic acid, and polymerizing that would be polyundecanamide. Industrial in Europe. Nylon 12, also industrial, reasonably common nylon. So here I'm simplifying the structure a bit for sake of ease here, but it's a lactam. This is 12-amino dodecanoic acid lactam. And again, since the amino group is on the last carbon, that'll be omega, and that'll be lauryl lactam. Lauryl being a 12-carbon carboxylic acid. Omega lauryl lactam. Polymerizing that, we get polydodecanamide, 12-carbon unbranched amide, or polymonomer is polyomega lauryl lactam. Note that as the distance between the amide group increases, that's the polar part, and we have longer stretches of nonpolar carbon groups, then the flexibility will increase, and of course the melting point would decrease as intermolecular attraction between chains decreases. Nylon 6,6, nylon 6,6 is the largest production polyamide in North America. It has many uses. So in this case, we have two different monomers. We have a diamine and a dicarboxylic acid. In this example, hexamethylene diamine is one monomer, and then hexane dioic acid is the other, and they'll polymerize to be follow with me, hexamethylene adipamide. Adipamide being the diamide of adipic acid. Or if you prefer, polyhexamethylene hexane diamide, strictly IUPAC. Now this can be produced from the carboxylic acid or from the acid chloride. It gives the same product here, either adipoyl chloride or adipic acid. So when it happens that there are two different carbon groups in the repeating unit, they're separated by a comma, in this example 6, 10, and the first carbon group identifies the number of carbons in the amine section, and the second carbon, those number of carbons that derive from the carboxylic acid. Getting still larger, nylon 610. Again, hexamethylene diamine gives us a 6-carbon diamine, and then sebacic acid or decane dioic acid gives us the 10-carbon carboxylic acid piece, and that would be polyhexamethylene sebacamide polymer, aka polyhexamethylene decane diamide polymer. Nylon 612, again hexamethylene diamine and dodecane dioic acid, an extract of castor oil. On condensation will produce the polyamide polyhexamethylene dodecane diamide. I make the case again is the more of these they do, the easier they become. You see the pattern in them. Now, nylon 6T refers to a polyamide made with 6 carbons from the diamine, and the dicarboxylic acid is terephthalic acid. That is 1,4-benzene dioic acid. Let's digress here for a second. Do you recall this structure, KHP, potassium hydrogen phthalate, KHP? Yep. Okay, so KHP is the half neutralized salt, potassium salt, of 1,4-benzene dicarboxylic acid, whose common name is terephthalic acid. If the carboxylic acid groups are in the ortho position to each other, it's named orthophthalic acid. If the carboxylic acids are in the meta positions, unfortunately it's not named metaphthalic acid. For some reason it's called isophthalic acid. This is 1,3-benzene dicarboxylic acid. So this is where these names derive from, many from the common system. Alright, so back to here. This then you recognize as being terephthalic acid. And a dicarboxylic acid and a diamine can be condensed together to produce a polyamide. This would be polyhexamethylene para or P benzene diamide, or more simply polyhexamethylene terephthalamide. So those are some aliphatic polyamides. There's a lot of them. Nylons are commercially important. Now, aramids are fully aromatic polyamides. They are not called nylons. Here's one, probably the most famous one. This will be 1,4-benzene diamine, we could say P, or paraphenylene diamine, with 1,4-benzene dioyl chloride. So here we're using the acid chloride. This would be terephthaloyl chloride instead of terephthalic acid. Well, this condenses to produce Kevlar. Kevlar would be poly p-phenylene terephthalamide. And this is completely linear and completely aromatic. All the carbons come from the aromatic monomer. It's used to make bulletproof vests. It's rigid. It has the highest melting points among thermoplastics, 500 degrees Celsius. That's actually incredible. I'm just calculating that 500 times 1.8 is 900 degrees Fahrenheit, exceedingly high melting point for a thermoplastic. And it's owing to the frequency, the high density of polar amide bonds, and the chains that are completely linear and line up very well. So this will be pulled as a fiber to stretch out the chains into to alignment to give maximum intermolecular attraction of these polar hydrogen bonded groups. If, on the other hand, the monomer has the acid chloride groups not para but in other positions, we get a much less straight chain, and it lowers the intermolecular attraction. So the orthopolymer has a melting point of only 200 to 300 degrees Celsius. Now here's the meta disubstituted monomers. So we have 1,3-benzene diamine and 1,3-benzene diol chloride, or metaphenylene diamine isothalloyl chloride, and this gives a similar product. This one's called Nomex, and notice the melting point is a little lower than the Paro 365. This would be polymetaphenylene isothallamide. Occasionally polymers are blended together. We might have a blend of 6,10 and 6,6 together. So lots of applications. So on page 117, let's then look at some of the properties and applications of nylons. And I think before we read some of this, well, let me read this first. Nylon 6, nylon 6,6, Kevlar. Well, Kevlar sets itself apart, but look at nylon 6 and 66. Denser than water, denser than hydrocarbons, of course. Relatively strong, high tensile strength, relatively stiff. Pretty high melting point because of the polar hydrogen bonded amide groups. High water absorption and relatively expensive. Kevlar stands apart, extremely strong, extremely stiff, extremely high melting. Take a look at the pictures and then we'll come back and read some of these words. So as we read these, think about these products that you're familiar with. These are polyamides. So we've seen, no doubt, active sportswear made of nylon blazers and jackets. Perhaps you've seen monofilament fishing line made of nylon bristles from your toothbrush, nylon tents. And down here we have applications of Kevlar. No doubt your bulletproof vest is made of Kevlar, as is your kayak or canoe, of course, to save you a lot of weight in lifting it. High strength, low weight, so high strength to weight ratio, even cut-proof gloves. Let's go back and look at some of those properties now of nylons. Nylons are strong, they're tough, they're abrasion-resistant thermoplastics. They are engineering resins. They're self-extinguishing when ignited. That's a good thing. They're very polar because of the amide groups. They have hydrogen bonding. This results in strong intermolecular hydrogen bonding and tight packing. They are translucent. That's not transparent, but like the visor on a light fixture. They allow light to pass, but they'll distort the image. They're translucent or pale white. Why? Because they're not amorphous. They have high crystallinity. Nylons have relatively high water absorption, again because of the amide functional groups, especially true with short chain hydrocarbons like nylons 3 and 4. Nylons have natural anti-friction properties. They're slippery, not as slippery as Teflon, but not far behind. They have low gas and vapor permeability, and so they are FDA approved as food packaging material. Now, the longer hydrocarbon nylons have greater flexibility, lower melting points, and lower water absorption, expectedly, because there's more hydrocarbon content. In terms of chemical resistance, nylons are resistant to non-polar solvents like gasoline, for example, oil and grease. It's good. Even ammonia, acetone, but they are attacked by oxidizers like chlorine and peroxides, and of course something of similar nature, amide and formic acid, and UV light attacks many polymers. Some of the applications we've already alluded to, but kind of summarize it here. Nylon 6,6 is the largest production volume of the nylons, and nylon 6 is second. Together they comprise 90% of all nylon products. So think of some of these materials that you probably see in everyday life. Aliphatic nylon molded or extruded parts, like gears and rollers. So for example, next time you pull a drawer out of a file cabinet, look at what it's rolling on. The glides and rollers typically made of something like nylon. They're tough and hard, but low friction. Bearings, circular bearings, if they're not steel, likely for something of lower weight category, be nylon bearings. Drapery slides, zip fasteners, zippers on your jackets, if they're not a metal, they're likely nylon. Cooking bags, tubes, rods, electrical cable, insulation, and housings for structural parts and machines and appliances and electric razors and such. Then we have fibers. Think of brushes, bristles, carpets and hosiery, apparel, surgical thread, parachute fabric, rope, tents. Your tent is woven from nylon fibers. PVC coated rainwear. So the raincoats that you have, that's a nylon fiber that's coated with PVC. Reinforcements in hoses and belts and tires. So your tires have what they call belts in them. They're actually made of nylon fibers or steel belts sometimes. And then finally here we have Aramid fibers, high performance fibers. The outstanding strength and stiffness and thermal resistance of aramid fibers results in their use as a reinforcing agent in epoxy and other composites for fishing rods and golf club shafts and tennis rackets and skis. If you're into high-tech sports equipment, you'll see it here. Airplane flaps, rudders, bulletproof vests, crash helmets, race car bodies, and helicopter fuselages. So many important uses and applications for nylons. So that ends our lesson on polyamides.